Hello and welcome. In this video, we will explore the powerful techniques of manipulating Maclaurin series, a key topic in IB mathematics analysis and approaches higher level. By the end of this session, you will be able to, first, find Maclaurin series for composite functions using substitution. Second, perform arithmetic operations like addition, subtraction, and multiplication on series. Third, differentiate and integrate series term by term. And finally, use these methods to solve complex problems, including finding limits and approximating integrals. We'll begin by recalling the fundamental Maclaurin series that form our toolkit. Let's start by listing the essential Maclaurin series you should be familiar with. These are the building blocks for everything we'll do. First, the geometric series for 1 over 1 minus x, which is the sum of x to the power of k, or 1 plus x squared, and so on. This is valid for the absolute value of x less than 1. Next, the exponential series for e to the power of x, which is the sum of x to the power of k over k factorial. This is 1 plus x squared over 2 factorial, and so on. This series converges for all real numbers x. Then we have the sine series, which is the sum of -1 to the k times x to the 2k plus 1, all over 2k plus 1 factorial. This gives us x minus x cubed over 3 factorial, and so on. Like the exponential series, it converges for all real x. And the cosine series, which is the sum of -1 to the k times x to the 2k, all over 2k factorial. This is 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial, and so on. This also converges for all real x. Finally, the binomial series for 1 plus x to the power of p. This is 1 plus p x plus p times p minus 1 over 2 factorial times x squared, and so on. This series is valid for the absolute value of x less than 1. These 5 series are the foundation for the techniques we'll be learning today. Let's see how we can use them. Our first technique is substitution. This is a very efficient way to find the Maclaurin series for composite functions. The idea is simple. If you have a known series for a function f of u, you can find the series for f of g of x by replacing every u in the original series with g of x. Let's work through an example. Suppose we want to find the Maclaurin series for e to the power of 2x. We know the series for e to the power of u is 1 plus u squared over 2 factorial, and so on. Here our inner function g of x is 2x. So we substitute 2x for every u. This gives us 1 plus 2x plus the quantity 2x squared over 2 factorial plus the quantity 2x cubed over 3 factorial, and so on. Simplifying the terms, we get 1 plus 2x plus 4x squared over 2 factorial plus 8x cubed over 3 factorial, and so on. This is the Maclaurin series for e to the power of 2x. Let's try another one. Find the Maclaurin series for cos of x squared. We start with the series for cos of u, which is 1 minus u squared over 2 factorial, plus u to the 4th over 4 factorial, and so on. This time, our inner function is x squared. Substituting x squared for u, we get 1 minus the quantity x squared over 2 factorial, plus the quantity x squared to the 4th over 4 factorial, and so on. Simplifying the exponents, we find the series for cos of x squared is 1 minus x to the 4th over 2 factorial, plus x to the 8th over 4 factorial, and so on. Notice that this series only contains even powers of x. So we've seen how to use substitution to find series for composite functions. This is a powerful and efficient method. Now, let's explore how to perform arithmetic operations on Maclaurin series. We can add, subtract, and multiply series just like polynomials. The key principle is that we can add or subtract 2 series term by term. For multiplication, we use the distributive property, multiplying each term of one series by each term of the other. Let's start with addition. Find the Maclaurin series for sin x plus cos x up to the x to the 7th term. We write out the series for sin x and cos x. Then we group the terms by their power of x. The constant term is 1, the x term is x, the x squared term is negative x squared over 2 factorial, the x cubed term is negative x cubed over 3 factorial, and so on. We simply combine the coefficients of like powers of x. Now for multiplication. Let's find the first 5 non-zero terms of the Maclaurin series for e to the x times sin x. We write out the first few terms of each series. To find the first 5 non-zero terms of the product, we need to multiply enough terms to get up to the x to the 4th power. We multiply each term of the e to the x series by each term of the sin x series. For example, 1 times x is x. X times x is x squared. X squared over 2 factorial times x is x cubed over 2 factorial. We continue this process, being careful to only keep terms up to x to the 4th. Now we collect the like terms. The x term is x. The x squared term is x squared. The x cubed term is negative 1/6 plus 1/2, which is 1/3. The x to the 4th term is negative 1/6. So, the first 5 non-zero terms are x plus x squared plus x cubed over 3 minus x to the 4th over 6. This method of multiplying series is a reliable way to find the first few terms of a product. One of the most powerful properties of Maclaurin series is that they can be differentiated and integrated term by term. This means we can find the derivative or integral of a function by simply differentiating or integrating each term of its series individually. This is incredibly useful for functions that are difficult to differentiate or integrate directly. Let's see this in action. We know the series for cos x. Let's find the series for sin x by differentiating the cos x series. We start with the series for cos x. We know that the derivative of cos x is negative sin x. So, negative sin x is equal to the derivative of the series for cos x. We differentiate each term. The derivative of 1 is 0. The derivative of negative x squared over 2 factorial is negative 2x over 2 factorial. The derivative of x to the 4th over 4 factorial is 4x cubed over 4 factorial, and so on. Simplifying the terms, we get negative sin x equals negative x plus x cubed over 3 factorial minus x to the 5th over 5 factorial, and so on. Multiplying by negative 1, we recover the familiar series for sin x. We can also integrate. Let's find the series for arctan x by integrating the series for 1 over 1 plus x squared. First, we find the series for 1 over 1 plus x squared using substitution. We take the geometric series for 1 over 1 minus u and substitute negative x squared for u. This gives us 1 minus x squared plus x to the 4th minus x to the 6th, and so on. Now we write down the integral we need to solve. Now we integrate this series term by term. The integral of 1 is x. The integral of negative x squared is negative x cubed over 3. The integral of x to the 4th is x to the 5th over 5, and so on. We also get a constant of integration, c. To find c, we can set x equals 0. We know arctan of 0 is 0. The series also evaluates to 0 at x equals 0. Therefore, c must be 0. This gives us the Maclaurin series for arctan x. This method of differentiation and integration is a cornerstone of working with Maclaurin series. Let's now apply these techniques to solve a more complex problem, similar to what you might see in an IB exam. We are asked to find the first 2 non-zero terms of the Maclaurin series for cos of e to the x, and then use this to find an approximation for x near 0. This is a composite function, so we'll use substitution. We'll substitute the series for e to the x into the series for cos u. We start with the series for cos u. Then we substitute the series for e to the x for u. This gives us 1 minus the quantity 1 plus x, squared over 2 factorial, and so on, squared all over 2 factorial plus higher order terms. Now we need to expand the term in the parenthesis, but we only need to go up to the x term, because we are looking for the first 2 non-zero terms. Expanding the square, we get 1 plus 2x plus x squared, plus higher order terms. Substituting this back into our expression, we get 1 minus 1/2 times the quantity 1 plus 2x plus x squared, plus higher order terms. Distributing the negative 1/2, we get 1 minus 1/2 minus x, squared over 2, and so on. Combining the constant terms, we get 1/2 minus x squared over 2. This is the beginning of our series. Now the problem asks us to show that this is approximately cos 1 minus sin x. This suggests we should use the direct calculation method to find the Maclaurin polynomial of degree 1. The Maclaurin polynomial of degree 1 is given by f of 0 plus f prime of 0 times x. Let f of x be cos of e to the x. First, we find f of 0. This is cos of e to the 0, which is cos of 1. Next, we find the derivative, f prime of x. Using the chain rule, this is negative sin of e to the x times e to the x. Evaluating at x equals 0, we get negative sin of 1 times 1, which is negative sin of 1. Substituting these values into the formula for the Maclaurin polynomial, we get m sub 1 of x equals cos of 1 minus sin of 1 times x. This matches the approximation we were asked to show. This example demonstrates how to combine substitution with direct calculation to solve a multi-part problem. Let's tackle another common application, using Maclaurin series to evaluate limits. When you encounter a limit of the form 0 over 0, you can often use L'Hopital's rule. However, substituting Maclaurin series for the functions involved can be a much faster and more elegant method. Consider the limit as x approaches 0 of the quantity e to the 2x minus 1, all divided by sin of 4x. If we substitute x equals 0, we get e to the 0 minus 1 over sin of 0, which is 0 over 0. This is an indeterminate form. Now let's substitute the Maclaurin series for the numerator and the denominator. For the numerator e to the 2x minus 1, we use the series for e to the u with u equals 2x. This gives us 1 plus 2x squared over 2 factorial, and so on, minus 1. The 1's cancel out, leaving us with 2x plus 2x squared plus higher order terms. For the denominator, sin of 4x, we use the series for sin u with u equals 4x. This gives us 4x minus 4x cubed over 3 factorial plus higher order terms. Now we substitute these series back into the limit expression. We have the limit as x approaches 0 of the quantity 2x plus 2x squared, and so on, divided by the quantity 4x minus 64 cubed over 6, and so on. To evaluate this, we can divide both the numerator and the denominator by the lowest power of x, which is x. Dividing by x, we get the limit as x approaches 0 of 2 plus 2x, and so on, divided by 4 minus 64 squared over 6, and so on. Now, as x approaches 0, all the terms with x in them go to 0. We are left with 2 divided by 4, which simplifies to 1/2. This method is often much faster than repeatedly applying L'Hopital's rule, especially for more complex functions. Finally, let's look at how Maclaurin series can be used to approximate definite integrals, especially for functions that don't have a simple antiderivative. The process is to first find the Maclaurin series for the integrand, then integrate that series term by term, and finally evaluate the resulting series at the limits of integration. Let's estimate the integral from 0 to 1 of cos of x squared dx, correct to 4 decimal places. First, we need the series for cos of x squared. We found this earlier using substitution. It's 1 minus x to the 4th over 2 factorial, plus x to the 8th over 4 factorial, and so on. Now we integrate this series from 0 to 1. We integrate term by term. The integral of 1 is x. The integral of negative x to the 4th over 2 factorial is negative x to the 5th over 5 times 2 factorial, and so on. Now we evaluate this at the limits. At x equals 1, we get 1 minus 1 over 10 plus 1 over 2s16, and so on. At x equals 0, all terms are 0. So the value of the integral is approximately 1 minus 0.1 plus 0.463, and so on. To get the approximation correct to 4 decimal places, we need to sum enough terms until the next term is smaller than 0.00205. The first term is 1. The second is negative 0.1. The third is approximately 0.0463. The fourth term would be negative 1 over 13 times 6 factorial, which is about negative 0.0. The fifth term is even smaller. Since the fourth term is not smaller than 0.005, we need to include it. Summing the first four terms, we get 1 minus 0.1 plus 0.00463 minus 0.007, which is approximately 0.904523. Rounding to 4 decimal places, our estimate is 0.904. This method allows us to find accurate approximations for integrals that are otherwise impossible to solve analytically. Let's conclude with a final, more advanced example that combines several of these techniques. We want to find the Maclaurin series for the hyperbolic cosine function cosh x, and then use it to prove Euler's formula. First, let's find the series for cosh x. The definition of cosh x is e to the x plus e to the negative x, all divided by 2. We can find the series for e to the negative x by substituting negative x into the series for e to the x. This gives us 1 minus x plus x squared over 2 factorial, and so on. Now we add the series for e to the x and e to the negative x. The odd-powered terms cancel out, and the even-powered terms double. Dividing by 2, we get the series for cosh x, which is 1 plus x squared over 2 factorial, plus x to the 4th over 4 factorial, and so on. Notice this is the same as the series for cos x, but with all positive terms. Now for Euler's formula. We start with the series for e to the x and substitute I times theta for x. This gives us 1 plus I theta squared over 2 factorial plus I theta cubed over 3 factorial, and so on. Now we use the fact that I squared is negative 1, I cubed is negative I, and I to the 4th is 1 to simplify the terms. The series becomes 1 plus I. Theta minus theta squared over 2 factorial minus I. Theta cubed over 3 factorial plus theta to the 4th over 4 factorial, and so on. Finally, we separate the real and imaginary parts of the series. The real part is 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial, and so on. This is exactly the Maclaurin series for cos of theta. The imaginary part is theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, and so on, all multiplied by I. This is the Maclaurin series for sin of theta. Thus, we have proven Euler's formula. This beautiful result shows the deep connection between exponential, trigonometric, and complex numbers, all revealed through Maclaurin series. We have now covered the essential techniques for manipulating Maclaurin series. Let's quickly recap what we've learned. We learned how to use substitution to find series for composite functions, how to add, subtract, and multiply series like polynomials, and how to differentiate and integrate series term by term. We then applied these skills to solve problems involving limits and integral approximations. Mastering these techniques is crucial for success in IB Mathematics AAHL. Now let's test your understanding with some practice questions. Here are 5 practice questions designed to reinforce the concepts we've discussed. I encourage you to pause the video and attempt them on your own before watching the solutions. Question 1 asks for the Maclaurin series of sin of 2x. Question 2 asks for the first 3 non-zero terms of the series for tan x. Question 3 asks you to find a limit using series. Question 4 asks for an integral approximation. And question 5 asks you to find the series for arcs in x. Take your time and remember to use the techniques we've covered. When you're ready, continue the video for the solutions. Welcome back. Let's go through the solutions together. For question 1, we use substitution. We take the series for sin u and substitute 2x for u. This gives us 2x minus 8x cubed over 3 factorial plus 32x to the 5th over 5 factorial, and so on. For question 2, we use division. We set tan x equal to a series with unknown coefficients, a sub k. We then multiply by cos x and equate coefficients. This gives us a sub 0 equals 0, a sub 1 equals 1, and a sub 2 equals 0. The first 3 non-zero terms are x plus x cubed over 3 plus 2x to the 5th over 15. For question 3, we use series for the limit. The series for cos of x squared is 1 minus x to the 4th over 2 factorial plus higher order terms. Subtracting 1 gives negative x to the fourth over 2 factorial. Dividing by x to the fourth and taking the limit as x approaches 0, 0, we get negative 1/2. For question 4, we approximate the integral. The series for e to the negative x squared is 1 minus x squared plus x to the fourth over 2 factorial, and so on. Integrating term by term from 0 to 0.5, we get 0.5 minus 0.5 cubed over 3 plus 0.5 to the fifth over 10. This gives an approximation of 0.48. For question 5, we integrate the series for 1 over the square root of 1 minus x squared. This series is found using the binomial expansion. Integrating term by term and setting the constant of integration to 0, we get the series for arcs in x. I hope these practice questions and solutions have helped solidify your understanding of Maclaurin series manipulation. Keep practicing and you'll master this topic.